The mirror equation is 1 over dO plus 1 over di equals 1 over f. So that's 1 over the object distance plus 1 over the image distance equals 1 over the focal length. For our diagram, let's pick some nice numbers that kind of match our picture here. Let's imagine we have a focal length of, let's say, 2 centimeters. This would actually be a smaller diagram, but to scale it'll be okay. So we'll say f is 2 centimeters. Well, if that's 2 centimeters, this would be 4 centimeters. This must be 8 centimeters. So keeping with our diagrams, we'll say we have an object distance of 8 centimeters. Let's use the mirror equation to figure out what the image distance is. If 1 over dO plus 1 over di equals 1 over f, then 1 over di must be 1 over f minus 1 over dO. In other words, 1 over 2 centimeters minus 1 over 8 centimeters. 1 over 2, that's like 4 over 8. 4 over 8 minus 1 over 8 is 3 over 8 centimeters. That's 1 over di. So di must be the inverse of that, which is 8 over 3 centimeters, which is 2.67 centimeters. Well, let's look at our diagram. If this is 2 centimeters, if this is 2, and that's 4, 3 would be right around here, and we notice, well, yeah, that looks like it's about 2/3 of the way between 2 and 3, which would be 2.67. 2 and 2/3, 2.67 centimeters. Very good. So this matches our diagram. We have another relationship, and that tells us the magnification of our image. The magnification is equal to minus di over dO. So what do we get in that case? We get the magnification is minus di, which is 2.67 centimeters, over dO, which is 8 centimeters, or negative 0.333. If you just leave it in your calculator, this would be 2.666666666 divided by 8, and that's 0.333. But if you put it actually as 2.67, you might get 0.334. That doesn't really matter. Notice that the units cancel for the magnification. The magnification is a unitless quantity. But it's negative. What does the negative tell us? The negative sign tells us the image is inverted. So looking at the magnification, that tells us it's inverted. And look at that, negative 1/2, 1/3. Actually, we were very close. When we said 1/3, that was exactly right, negative 1/3. So the magnification really is negative 1/3, and that really does look like it's closer to 1/3 than 1/2. Now, how do we know whether the image is real or virtual? If we look at the image distance, a real image will have a positive image distance. A virtual image will have a negative image distance. And in our case, we found that di was positive. That tells us we have a real image. So we look up here, real image, yep, that's exactly what we got because we found that di was positive. An inverted image, yep, that's exactly what we got because we got a negative magnification. And m is negative 1/3, and that is just what we got. Woo! That is just what we got. Very, very good. Let's take a look at the other kind of mirror. Let's look at a convex mirror and see how that affects these diagrams. Here I've drawn a convex mirror. I've left our 3 principal rays up there for our concave mirror because we're going to come back to these and only change what we need to for the convex mirror. So I'll just leave those up there for the time being. Here is our convex mirror. Again, it's a part or an arc of a sphere that has a center. So I'm going to draw that in, the center of the sphere of which our convex mirror is an arc. I'm going to draw a line from the center through some midpoint of our mirror, and I'll refer to that as our principal axis. We're going to analyze this just like we did with the concave mirror. Let's first look at rays that come in not from the center, but in this case toward the center. Imagine that we have a ray coming in toward the center, and I'll just dot this over here to indicate it's actually going toward the center. What is that ray going to do? Again, it's going to reflect off with an equal angle of incidence as reflection. We know that the tangent line will have a normal line that points towards the center. which means what is the incident angle for a ray that is approaching the center? If this is the normal line and the incident ray is coming right along the normal line pointing toward the center, the incident angle is 0. So what's the reflected angle? It is also 0. So how is the ray going to reflect? It's going to reflect right back out from the center. So the ray comes in and reflects right back out on itself. Toward the center, away from the center. And again, it doesn't matter where this ray is, as long as the ray comes in toward the center. I'm trying to draw these toward the center. However it goes in, it's going to reflect right back out on itself. As long as it approaches the center, it reflects right back on itself. Very good. Let's take a look at another ray. Let's look at a ray that comes in parallel to the principal axis, just like we did for the concave mirror. Here I've drawn in our incoming ray parallel to the principal axis. Here I've drawn in our normal line that comes from the center. So here's our normal line here. We know the ray will reflect so that we have an equal angle of incidence and reflection. So we know those two angles are equal. Going inside the sphere, we know this line is straight here and this line is straight here. So we know that angle must equal this angle in here. So those three angles are all the same. We also know that this ray, which is this ray here, the normal line, which is crossing these two parallel rays, this angle must be the same as this angle. So again, we know those angles must be the same. Once again, we have an isosceles triangle, so that this length must be the same as that length. Again, we're going to make an approximation that the incoming ray is close to the principal axis. What does that mean, close to the principal axis? It means that the distance between the ray and the principal axis is small compared to the radius of the mirror. And again, just before we end, we'll take a look at that approximation in just a minute. We're going to make that approximation, which again means this triangle is very, very small, which means this side of the triangle is very short, which means this length of the triangle is very, very close to that length, which is the approximation we're going to make, which tells us then that this length is the same as that length, which means this point is very close to the midpoint between the center and the mirror. And once again, we're going to call that the focal point or the focus for our convex mirror. What's this mean? It means that for an incoming parallel ray, and again, we are always going to make this approximation now, that is close to the principal axis. The distance is small compared to the radius. For an incoming ray parallel to the principal axis, it reflects off the mirror, not through the focal point, but from the focal point. Very, very good. This is a very important difference from our concave mirror. And you might guess, we're going to use this as our first principal ray when we draw a ray tracing diagram. Let's go ahead and change our first principal ray right now. A ray that comes in parallel is then reflected from the focal point. Well, how do we have to change our ray from the concave mirror? For the concave, we had in parallel out through the focus. Well, we don't have to change this very much. All we have to do is say in parallel out from the focus. And let's remember, that's the difference that we have to make, the only difference. In parallel out from the focus. What about our second ray? Well, remember, our second ray is just a reversal of the first one. We know that a ray that comes in parallel is reflected from the focus. Well, how do we reverse that ray? We reverse these directions, and what do we get? A ray that comes in not through the focus, but in toward the focus, reflects out parallel. How do we change our second principal ray? In through the focus, out parallel. Well, again, all we have to do is change one word. In toward the focus. So in toward. In toward the focus, out parallel. Very, very good. Very small change. What about the third principal ray? The third principal ray will be the one that deals with the center, just like we did before. What's that? Remember that a ray that comes in like this towards the center will be reflected back out from the center. How do we change this? In through the center, out through the center? Well, again, all we have to do is change two words here in this one. In toward the center, out from the center. Very, very minor changes from the concave to the convex mirror principal rays. Thing to keep in mind, though, is for both of them, it's parallel and then something to do with the focus. And then something to do with the focus and parallel. And then center and center. That's the same for both concave and convex. The directions are just what you have to keep track of. Okay? Remember, for the convex, in parallel, out from the focus, in toward the focus, out parallel, and then in toward the center, out from the center. Very good. Let's try this with a ray tracing diagram for a convex mirror. But again, one more thing. Assuming we're close to the center, we're going to draw our mirror as a straight line. And in this case, so a straight line, there's our mirror. Again, we're going to draw it as a straight line. But in this case, because the curvature is in that direction, I'm going to put our tabs going the other way. So the light is over on this side striking the mirror, and the mirror is then curved that way. Again, anytime you draw a ray tracing diagram for a convex lens, make sure you draw the mirror, convex mirror. Make sure you draw the mirror as a straight line and put your tabs going away from the side where the light is. And you should recognize anything that you see that's drawn like that is going to be a convex mirror. Very good. Let's give this a try and see what we get.